Everyone, July the 5th. Alright, news today is not gonna defend my dissertation this summer. Have to delay it. It's alright. It was originally just we shooting for the moon, right? We trying to see if it's possible, but it turns out it's not. Mainly the logistic. It's just so hard to get everybody on the same page with 3 weeks notice. And I mean, honestly, the dissertation, the quality could have been improved if we wait a little bit more. We have more time to get a little bit better, into a better shape. So overall, I think it's not too bad an idea that we delay it. And I mean, that does mean we'll have to stay for one more semester, but life happens, so it's okay. Well, we're gonna do this one for today for sure, but I have no idea how to do this one. I tried to think about it last night a little bit more. It feels to me is segment tree, but I just can't think of a way to convince myself that segment tree can work. That's the thing, right? I just couldn't figure out. Like, there are so many segments going around. I need to figure out how the segment works. And at the moment, I don't know. Right? I just don't know how the segment can work. And in my mind, things can move around so much. So your segment is getting broken up and recreated. So I don't know how I should. And I have kind of the idea how this should go, but I really don't know how in reality this one shall work. Like, I know this, it's nothing, but it's just a length, right? Yeah, because of the length, you can calculate their positions after they move without actually moving them. But every time you pick the smallest, right? The current smallest. It's like part of the segment will get updated, right? While the other part does not. And it's just which part needs to get updated. That one is really giving me a hard time at the moment. I don't know. I might give up, but I don't know. Let's get this one done first, and then we go back to the other problem. Minimum size subarray sum given an array of positive integers and a positive integer target. Return the minimum length of a subarray whose sum is greater than or equal to target. If there's no such subarray, return 0. So in this case, we have a target 7, so we need for 3 exactly. 4 will be just 1. 11 will be 0. Okay. If you have figured out the ON solution, try coding another solution of which the time commencing. If I know ON, why do I need to do an ON log n? But anyway, so maybe we can try ON log n first. I mean, you are asking for a subarray with a minimum length. So what I can think about is binary search, right? You can start with a whole length, and then you can start with half a length, and you do sliding window at every single one, and see if it's larger or equal to this, and you try to get a smaller, and if it's not, you try to get bigger. So that definitely works. ON log n. You know what? Maybe we can try the ON log n first, because ON log n is the most obvious one. So for me, ON log n is the most obvious one, right? And we can say low high equal to 0 high. Let's do len nums, okay? And then we say while low is smaller than high, mid, low plus high divided by 2. Now we just need to do a sliding window with the size mid. And how do we do a sliding window with size mid? What we can do is, so we can have the count 0, okay? So we can say sliding window ij. Okay, so start. Oh, I can just use start, I don't need to use count, right? And then we can say, let's call it I. So for j, in range, len nums, you know what, for j, and enumerate nums, okay? Then we say if j minus I plus 1 is smaller than mid, then we can what we can do, we need a sum, so current sum s. Okay, I think what I should do is just to add it. Okay, so just s plus equal to n. Okay, and if j minus I plus 1 is larger than mid, then s minus equal to nums I, right? Because it's too much, so we do a minus, right? And then we shall say if j minus I plus 1 is equal to mid. That's the case, then we can check. Then we say if, so we want the minimum length, right? So if as long as one of them is good, right, we should shrink. So we say if s is if s is larger or equal to target, right, then we shall be able to get smaller. So say high equals to mid, then we break. If it's smaller, then we don't do. So when we else, which means no one is larger, so then we need to make it bigger. So we say low shall equal to mid plus 1 and continue. How do you mean continue? I just say do this, right? So blah blah blah. Once we're done, right? Once we're done, so I think I shall return minimum length. Let's just return low. Let's give this a shot. This is 2. This is going to be 1. This is going to be 0. Oh, 0. Not sure if we can do 0. So target nums that was pretty bad. How? All right, let's analyze it. That was pretty bad. Result is 4. How is result is 4? Well, we start with half, so high will equal, let's just take a look at the low and high. 0, 6. Wait, nobody is larger than target? That's bonkers. Oh, I forgot to increment I. Oof, that's bad. So every time this should be I plus equal 1. There we go. Forgot to increment the front. All right, the last one. We should do the last one. Well. So when it's too bad, low equal mid plus 1, low blah blah blah. So we will end up with taking everything, right? So that we shall probably say if sum nums is smaller than target, then return 0. Because as long as the sum is larger, then we always have an option. So let's try this. Maybe we can try this. Just give it a shot. Okay, let's try this. See if this one works. Okay, this one works. So open login works, right? All right, this is binary search. Open login. Okay, now let's try to find the ON solution. What do you think is the ON solution? Well, ON solution is maybe, I don't know. Like something Cardane wise? What do you think? So we can say if at each position, okay, we record the length. Maybe not. Minimum length, right? So if at each position I have all the sum, right? And then this one comes, the new one comes in, and I can, you know, just check. That's the ON solution. Hold on, let me write it out. 2, 3, 1, 2, 4, 3, right? So the largest, you know, the length is 1, and the largest, okay, previous, the largest size is 2, and then you just look at yourself, and this will be 5, this will be 6, right? This will be 6, and then here, and say it will be 8, so you know this one definitely will work. Well, what is the length? Like this is also 7. Right? How do you know? I mean, if we do prefix sum, right, and then we have a certain position, prefix sum. Oh, we can do prefix sum. That's open login as well, right? Prefix sum 2, 5, 6, 8, 12, and 15. Not 15. Yeah, 15. Right? And at each one, I can say, let me do minus target. Right? So like here, minus target is 1. So we need to find something that's smaller than 1. So we can binary search this thing to find where it is. So 1, we don't have something smaller than 1. So that's, you know, not going to work. This minus 7 is 5. So we have a 5. Right? We have a 5. So the difference of these will be 3. And for this, minus 7 is 8. Now we have an 8. So maybe that's the ON login. Okay, we can try that. Let's try that. So solution 2 is still ON login. From iter tools, import accumulate. P-sum, right? List accumulate nums. Okay. Then we need a binary search. So from bisect. I want to do bisect right. Then we say for P in P-sum. Oh, yeah, we can say if p sum -1 is smaller than target, then we return 0. And if p is larger equal to target, well, nums is 1, so that's actually, it's not going to be target, but that's fine. Then we say index equal to bisect right p sum and p minus target. Right? So then we say if index is larger than, right? If index is larger than 0, because a 0, that's not going to work. If it's larger than 0, then res, right? Res equal to minimum res and we need I. Right, so it would be I minus index. Do I need to -1? So 0, 0, 1, 2, 3, 4, 5. 5 minus 3 is 2. Yeah, I don't need to -1, just do this. And then we return res. Okay, let's take a look. Solution 2. Ooh, almost. Oh, hold on. It shouldn't be index -1. Yeah, because index is on the right hand side, so it should be -1 because we need to minus the 1 on the left hand side. What if it's equal to? Yeah, you have to think about equal to. What if I have something equal to? I mean, in this case, it is equal to, because 12 minus 7 is 5, right? So I want to land on this, because if it's something, because it has to be something smaller, so I shouldn't be yes, because I land here, so it should be -1. Yeah, it should be -1 because it has to be something smaller than the difference. So yes, so it has to be -1. Yeah, let's just do this +1. Okay, so this is prefix sum and binary search. It's still O(n) log n, but what is the O(n) solution? Ooh wee! We have an issue with 1. Inf. Alright, let's not do inf. Randoms. Good check. Oh, that's not right. That's not right. Yeah, I kind of realized that's probably not a good way to go. Hold up. Expected to. Oh, it's the front, right? It's the front. Well, I could, because so what if I have accumulate and initial equals 0? It's not initial. What's that? Initial. Yep. We have to put a 0 at the beginning. Then we avoid the problem of the one we just said. But in that case, I think this probably can do math.inf. Yeah, you can do math.inf. It doesn't really matter. You can do math.inf. All we need is to have a initial equal to 0. Okay, it's faster, but again, what is O(n) log n? What is O(n)? O n. We want to find the smallest. Did I figure out the O(n) solution myself last time? I don't know. O(n) solution. What's the binary search, sliding window, prefix sum? These are all O(n) log n. Alright, let's take a look at what I had in the past. I have no idea what I did. I think this is... Now, is it bisect? Oh, you can use this. Yeah. This is O(n) log n. What's this? Oh, sliding window. Okay, for O(n). Sliding window for O(n). Alright, I try not to see it. Sliding window. How are you sliding window this for O(n)? Sliding window for O(n). So you have the current. So you try 1. Okay, if it's not enough, so you... Oh, maybe. Hold on. Maybe what it's trying to say is you can start with 2. Okay, too small. We add 3. Not enough. We add 1. Not enough. We add 2. Boom. That's the first one. Once we're done, we just start at minus. And this is smaller. So now we add 1. Boom, we get it. Now we minus this. Boom, we get it again. And we reduce. So that's too small. So we add this. We got it. Minus this. We got it. Then minus. Oh, I think that is the sliding window. I think I remember. I mean, doesn't count. I did check the solution. I checked the sliding window. I didn't see the implementation. I just checked the hint. Okay, so for sliding window, basically what we're gonna do is just to build up a sliding window that results in the sum that's larger than the target. Once we get there, then we can get rid of the left, right? We get off the left because it's already enough. So we get off the left. Every time we get off the left, we check, right? If it's still within the, if it's still larger than target, if it's still, we just, we update in the result until it's getting smaller, right? If it's getting smaller, yeah. So I think the idea is if you give me a sliding window, if it's not enough, so I have to keep adding until it's enough. Once it's enough, I don't have to keep adding on the right. I just need to reduce on the left to make it small, right? And then we can keep adding on the right. Okay, so let's just implement it. How are we supposed to implement? I have a result. Okay. This is a result. Maybe. Let's do result is this. Then what? Then we have a low and a high, and then we start everybody at 0. Okay. Then I just say, actually no. The high will always go out on the right hand side. So I just say I equal to 0. That's a low. And then for j, n enumerate nums. That's fine, right? And then I need a current s. So we can do s is also this, right? So we add s first, okay? S plus equal to n. We say while s is larger or equal to target, res equals minimum res j minus I plus 1, because that's the total length, right? Once we've done that, s minus equal to nums I, and then I plus equal 1, because I remove it. Then we try it again, Once it's done, we move on, j for the next one, then we j, add a new one, and then we remove this, and we'll return res. That is the O. Almost. So, all right, let's do math.inf, and we say return res if res is smaller than math.inf, else is 0. That is an ON solution. Yep, that's the ON solution. Oh, the size of the test case must be much bigger than before. Look at this. This is the current, and this is the previous time. 19 test cases. I have 20 test cases. Must have added a bigger one. You can see blah 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 p sum. That's fine. That's just s. And we do this. We do this. We do this. Yep, exactly the same. Okay, so we're done with this. Now what? Now we're back to this one. I don't know. I have to check. Easy sort solution. Sort count rotations versus BIT. Sorted list. Sort. So the hint now is to sort. Sort. How'd you do this with sort? Well, you get a hint. And try sort. Okay, -1, position 0, 1, 2. 3 position is 0. 4 position is 1. Okay, that's from small. So we know the first one we remove this. And next one we remove this. Now the things is when we remove this, we know its position. So this one takes 2 steps, right? We'll take 2 steps. No, remove, take 3 steps. We take 3 steps to remove this. And then 3, I see its position. What does that mean? I mean, I already find the previous one. Again, this is, I like to kind of visualize in this way, right? So we have this, I remove it. Perfect. And these things gets moved to the other side, right? So these gets moved here. And then let's say if I have the next smallest is here, then the number of removal I can compute that. Okay. If you are here, the minimum is here, then the number of removal, like how do you know the ones in front of you has to be removed, but these one has to be removed as well. So yeah, basically, how do you know how many you have to remove? And once you remove, this whole thing gets moved to the back. Hold on. Wait, hold on. When we do this split, okay? When we do this split, we have some on the front, we have some on the back, right? And I know the total number as well. I know my position, but yeah, it might get changed along the way. But I don't know how many is in front of me. I don't. What am I missing? -1 at position 2. Yeah. We remove the minimum, we split into 2 halves. Right? If the next minimum is on 1/2. Yeah, I guess this is not the right way to think. This is not the right way to think. Cycle from here to this, then to this. Hold a second. Let's try this one more time. If I have a range and I have the order, I say this one's the first one to move, this one the second, third, fifth. Okay, these are the order. Okay, so if I move this first, right, then I have to do all these steps. Okay, then I remove this, and the only thing that do not need to be moved is the ones in between, right? Because you move this part to the end, right? You move this part to the end, so this is your end. So whichever u towards the end now need to be moved. Okay, then you move this, right? Then you move this. Then the ones you do not need to move is this one towards the end. But since this part is already here, so when you move 0, okay, when you move 0, you need to do 1, 2, 3, 3 plus 1 steps, right? Yeah, this is a good example. Let's just write it out. Let's write it out. 4, 1, 3, 0, 2, 5. Okay. So first step when we're done will be 2, 5, 4, 1, 3. Right, and then we have 3 plus 1 step. And this we have remove 1. Right, so it will be 3, 2, 5, 4. That's also 3 steps plus 1. And then for 2, that's gonna be 5, 4, 3. That's only 1 plus 1 step. And then for 3, that's gonna be 2 plus 1 step. It's gonna be 5, 4. Right? And then that's gonna be 5. Just 1 step. 1 plus 1 step. And then empty as 1 step. Okay? So from this to this, right, 0 at here. So I have 3, when I know this position, we have 3 in the front, okay? And then this whole thing gets moved to the end, right? And I can say how many does now get moved. Well, I have here to here, I have 1 in between. That means the total length minus 1 will be the number of steps I need to take to get 1, okay? So now when 1 is gone, right, this is in the front. Now 2, okay? So 2, yeah, that's the problem. 2 is here. 1 is here. 0 is here. 2. The one to the right of 2 is only 1. but the things doesn't move is more. Yep, no idea. Come on. Let's take a look. I think it's probably is BIT, so I have to learn BIT on this one. Man, you kind of know it's BIT. It's segment tree, but wait, how does this solve? There are n elements at first, so there are at least n operations. And I take n operations, rotate all elements once. Record every element's position. Okay. Iterate all elements from small to big. Okay. If the position decreases, so we go from small value to big value, and we're looking at its position. If the position decreases, that means we have something smaller happening later. That means we need to rotate. Okay, I'm following you here. We need to rotate all remaining elements to the beginning. And this brings us back to out beginning intuition. What, dude? That was not English. We will increase rest by the number of remaining elements. Hold on. Is A take 3 up? Yes. If we insert 4, 5, 6, no matter what position, but keep their order. Now it takes 1 round to remove 4, 5, 6. Huh? What does it mean? Take 4, 5, 6. So it needs, well, it take 1, 2, and 3, 4, 5, 6. Yep. Look amazing. Got it. Alright, it doesn't make any sense. So we need 9 operation. Now we insert 1, 2, 3, no matter what position. We keep their order, so we need 9 plus 6. Huh? What is it trying to say? What it's trying to say is if we have something that's out of order, okay? If we have something that's out of order, then we'll have to, I don't understand. Let me read this again. all elements from small to big. If the position decreases, we'll rotate all the remaining elements. Yes, if the position decreases, so you're not saying that, hold on, so what you're saying is if it decreases, which means when this one gets removed, this has to go to the end, right? So we say when that happens, we have to record this step. This, we have to record this step. It doesn't make any sense. All remaining element to the beginning. All remaining to the beginning. What? I don't understand. Okay, so yes, we have to have end operation. That's just to remove the things. Okay, that makes sense. So now we're saying is as we go through this thing, as we go through this one by one, every time that the current value has index smaller than the previous value, which just means it has a bigger, right? It just means it has a bigger, no, let's just, hold on. Yeah, as we go through, if this value's index is smaller, because it's sorted, so if this value is smaller than the previous one, yeah, it's lower, then that means we'll rotate all remaining elements to the beginning. Why? Because I have something smaller, now I have something bigger to the left. So that's unnatural, so we remove everything from the beginning. Huh? Yes. 4, 5, so we have 6, right? And then in fact, how does this one work? This doesn't 4, 5, 7, 8, 9, 6, right? And the only time that the index for this it's smaller than the index of the previous one. So at first I record all the indices, okay? I record the indices. And then if the index of this, after we sort it, so after we sort it, 6 will come to here. Okay, so I start with 4, 5, 7, 8, 9, 6. So I get their indices. After we sort, 6 comes here, right? And after 6 comes here, this has a giant index. So this is fine, so we don't need to move. But this has a smaller index compared to this. So this has a bigger index, which means in this case, this thing has to go to the end, right? And when this thing go to the end, we basically is, we're sorting it, right? We're sorting it. But now I said, if this is smaller than this, then the remaining needs to move. The remaining needs to move. So you're saying whenever we encounter something that's out of order, okay? Because we want is for them to be sorted, right? If we sort them increasingly, then we just pop them out one by one. But in reality, they're not sorted increasingly. We have some, some smaller ones happens later, right? So the index goes down. So when that happens, when the index goes down, so that's the small one, and you cannot remove that directly. And when that happens, what do? You say, you'll take everything in the front, right? Move them to the back. Okay. Yeah, that's actually not right. That's actually not right. Whenever you find something small, right? Because you sort the whole thing. So if you find a mismatch in the index, you find a mismatch in the index, why do all the remaining needs to swap? Right, in this case, you have this has a smaller index compared to this. Okay, so this has a smaller index. So this one happens later on. Then you need to move this entire thing to the front. I don't know. I don't understand. All right, let's see people's explanation. Small into multiple passes. N is 8. Okay, so we split the process of removing small into 4 passes. Remove 1, 2, 3. Remove 4, 5, 6. Remove 7 and remove 8. That makes sense, right? That makes sense. Remove 1, 2, 3 from the array. We need to remove 1. Move 4 to the back. Move 5 to the back. Remove 2. Move 8 to the back. 7 to the back. 6 to the back. Remove 3. The first pass uses 8 operations, regardless what elements are in the first pass. Hold on, so we're breaking it down to stretches of sorted order, okay, from small to big. So whichever we want to remove, right, then it has to move the first stretch. So we're considering removing the first stretch from small to large, okay? And when we remove this first stretch, we have to move stuff, okay? We move stuff from front to back, okay? We move stuff from front to back, front to back, front to back. And we expose whatever we need to remove now, okay? And then we get it removed. Then how many we need to remove? What if, hold on, I still don't understand. I remove 1, that doesn't count, right? And then we'll move this to the back. So we have 1 step, 2 step, 3 step, 4 step, 5 step, 6, 7, 8 to remove everything. The first pass uses regardless of what elements are in the first pass. What? Regardless of what elements are in the first pass. What if my first pass is, what if, like in this case, what do you do? What's the first pass? 0? You cannot do 0, 2, so the first pass is 0. And we'll do 1 step, 2 step, 3 step. It should be just 4 step. 0, 1, 2, 3. 1, 2, 3, 4, 5, 6. 6 minus so I will be here, right? N minus I is the size of the remaining array. this. Let's keep reading. Remaining is this. I want to remove 4, 5, 6. Remove 4, remove 5, remove 8 to the end, 7 to the end, remove 6. Takes 5 operations. We'll sort it, okay. And if we sort it, after we sort it 0, 1, immediately we have a mismatch already because 0 happens after 1. So we say we need to remove 0. And to remove 0, the current position is 1, right? Is 1. Will be 5. We need to do 5 steps. But we actually only need 1, 2, 3, 4 steps. It still doesn't make any sense. Right? Because if you do this, if I sort this thing, 0 position is 0, 1, 2, 3. 1 position 0, 1. 2, 0, 1, 2, 3, 4. 3, 0, 1, 2. 4, 0. 5, 0, 1, 2, 3, 4, 5. Right? And we sort it. Okay, it's sorted. And then we go from this position. Okay, this position and the previous position. This is smaller, yes. The n minus I. 0, 1, n minus 1. So 5. Oh, hold on. 1, 2, 3, 4, 5, 6. So 6 minus 1. What is that? What is that? To remove what? Need 5 steps. And then we do this. We don't consider. Then we do this. But you don't take 5 steps to remove 0. Still don't understand. I understand the stretch, right? That does make sense. A stretch. So if we want to remove the stretch, we have to find out basically this position. Now I know this position. I need more explanation. Okay. Whether we remove an item or move to the next item, the cost of the operation is always 1, thus the end operations. When we find an item whose index is smaller than the previous, it indicates. Okay, so when this array, I think it's a sorted array, right? So you're going through a sorted array. If it's followed the indices, then you can remove. That's operations 1. If not, it's smaller than the previous. And we have iterated through the entire array. I must repeat the previous step again. That I don't understand. What does this mean? It's just a mismatch. We have a bigger one, right, happen here. Smaller ones in the front. Bigger ones at the end, right? So we hit the bigger one. Then we hit the smaller one. Wait, hold on, no. The small is in here, big is in here, right? So we So yeah, when we want to pop the small one, okay? On the pop the small one, that means the big one must have been counted already. Okay, that makes sense. The big one must have been counted already. So now, when we hit something, when we hit in a sorted array, so a big value, but it has a smaller index, which means the big value is in the front, but the smaller value is here. So if I go through this, then I go here. That means I'll keep thinking about this. I don't understand. I still don't understand. Even after reading the solution, I have no clue what it means. Alright, I'll get back to it tomorrow. I'll see you guys tomorrow. Adios.